Welcome to lecture 17A on bases and dimension for vector spaces. Recall that a vector space is a notion which generalizes a set of vectors, Rn. A vector space is a set where we have a rule for adding two elements in the vector space, and we also know how to multiply any element in the vector space by a number. Our motivating example is the set of vectors of height n. This is the vector space we have been working with most of the semester. We've also seen that the set of polynomials forms a vector space, and also the set of polynomials of degree at most n for any number n. The set of sequences is also a vector space, and then the set of matrices of the same size is a vector space, and the set of smooth functions form a vector space. And also the easiest way to build a new vector space is to take a subspace of a vector space. Recall that for a subspace of Rn, we have these three definitions, all involving linear combinations. For a spanning set, a linearly independent set, and a basis. If we have a set of vectors in a subspace, this set of vectors is called a spanning set for the subspace V if every element of V can be written as a linear combination in at least one way. The set of vectors is called a linearly independent set if every element of the subspace V can be written as a linear combination in at most one way. This set is a basis for the subspace V if it is a spanning set and also linearly independent. In other words, this set of vectors is a basis for V if every element of V can be written as a linear combination in these vectors in exactly one way. Now we will generalize this to a vector space. The definition is really going to be the same, except we can cross out Rn and replace it with a vector space. Linear combinations make sense in any vector space. In the previous lecture, we have done examples involving linear combinations in some vector spaces. So the definition is exactly the same. If I have a subset of elements in a vector space, then this set is called a spanning set if every element of my vector space can be written as a linear combination in at least one way. My set of elements is linearly independent in the vector space V if every element of V can be written as a linear combination in at most one way. And my set is a basis if it is both a spanning set for V and linearly independent. So my set of elements is a basis for V if every element of V can be written as a linear combination in exactly one way. Some of our tools from Rn generalize to general vector spaces. For example, we can check linear independence the same way. If we want to know whether a subset of elements in a vector space V is linearly independent, then what we can do is make a linear combination in terms of the vectors V1 through Vn and set it equal to the zero element in V. And we check that each of these coefficients must be zero. Let's work with some examples. In exercise 1, I will be working with polynomials. In this first exercise, I have a subset of polynomials in P1, and I want to check whether this set is a spanning set for P1. Recall first that P sub 1 is a set of polynomials of degree at most 1. So we can write every element in P1 as this polynomial for some numbers B sub 1 and B sub 0. To check whether our subset is a spanning set for P1, we want to check the following. I write down an arbitrary element from here on the left side, and then on the right, I will write down a linear combination of our subset S. Here, C1, C2, C3 would be my mystery coefficients, and I want to check whether this equation has at least one solution. So we want to be able to show that we would be able to find C1, C2, C3 no matter what B1 and B0 are. Right now, the right-hand side is not in standard form, so I will rewrite it so that it looks like the left-hand side. I want to put all of the terms that have an x together. So I should have C1 and C2 plus C3 here. And then for the constant terms, I should have 1 times C2 and then 2 times C3. Because of this equality, this means that B1 is equal to this sum and B0 is equal to this sum. We have a system of linear equations. So let's put this in augmented matrix form. Remember that here, the coefficients C1, C2, C3 are the variables we're trying to solve for, and B1, B2 are just arbitrary numbers that we have no control over. But because B1 and B2 are the numbers and not the variables we're trying to solve for, in the augmented matrix, we do keep the B1 and B0, but we don't have the C1, C2, C3 because C1, C2, C3 are our variables. Our augmented matrix is already in row echelon form, so we don't have to do any row reduce. We see that to the right of the vertical line, we do not see any leading one. This means that the system is consistent. The system being consistent means that we are able to find at least one C1, C2, C3 where this equality holds. Looking back to the definition of a spanning set, this means that our set is a spanning set for P1 because we have shown that every element in P1 can be written as a linear combination in at least one way. Now, if you're thinking ahead, you might notice that here, the third column does not have leading one. This shows that this system has infinitely many solutions. So this tells us that S is a spanning set for P1, but S is not a basis because the set is not linearly independent. In this next exercise, our vector space would be P, the set of all polynomials. We want to check whether this set is linearly independent. We will use this tool. We will write a linear combination of our 3 polynomials and set that to the 0 polynomial. And then we want to check, is it possible that we can get a linear combination where not all of the coefficients are 0 and still have the linear combination be equal to the 0 polynomial. Let me call this set T. First, I write a linear combination of the polynomials in T using C1, C2, C3 as my unknown, and I will set this to 0. We want to see if there are solutions other than having C1, C2, C3 be 0. If the only solution is C1, C2, C3, 0, then our set T is linearly independent. Otherwise, T is not linearly independent. Right now, this is not in standard form, so I will rewrite it by grouping x squared and x and the constant terms together. The terms that have x squared would be C2 and C3. So I have C2 plus C3 here. The terms that have just x would be C1 and negative C3. And the constant terms are negative C1 minus C2. The 0 polynomial is the same as 0 times x squared plus 0 times x plus 0. So this means that C2 plus C3 must be equal to 0, and then C1 minus C3 is equal to 0, and negative C1 minus C2 are equal to 0. So again, I get a system of linear equations. Let me rewrite this as a matrix multiplication. And then we need to do the augmented matrix. I see that there are non-zero numbers in the first column, but the first row has 0 in the first column. So let me swap the first and second row. Now the first row has a leading 1. I will make sure that all of the other entries turn into 0. Next, I see that the second row has a leading one. I will make sure the entry below gets killed. I now arrive in a row echelon form, and I see that I have these two leading ones, but not every column left of the vertical line has a leading one. This third column has no leading one. This means the system has infinitely many solutions. In particular, we have solutions other than the trivial solution. So our subset T is not linearly independent because the answer to this question is yes. In this next exercise, we'll work with the vector space P2 and check whether this set is a basis. This means we have to check that the set is a spanning set for P2 and also linearly independent. Recall that P2 is the set of polynomials of degree at most 2, so every element can be written in this standard form. So instead of checking linear independence and spanning separately, we can do both in one computation. We say let this be any element in P2, and we set this equal to a linear combination of our subset K, and we will count how many solutions this equation has. If this equation has 0 solution, this means that our subset is not a spanning set, and so it's not a basis. If the equation has exactly 1 solution, this means K is a spanning set and also linearly independent, so K is a basis. If we get infinitely many solutions, this means that K is a spanning set, but K is not linearly independent, so K is not a basis. Right now, this right-hand side is not written in standard form, so I do computation so that I can rewrite it in this way, where I have x squared x and the constant term. And this means that the number B2 has to be equal to this sum, and the number B1 has to equal to this sum, and B0 is equal to this sum. So I rewrite this as a system of linear equations, and then I rewrite this as this matrix multiplication. I will then rewrite this as augmented matrix and then row reduce. I then get this row echelon form. Because I'm not really interested in actually finding solutions, I'm just trying to count the number of solutions. I just need to check the leading ones. I see that the right column has no leading one. This is good. This means the system is consistent. And I check that every column to the left of the vertical line has a leading one. This means that there is one unique solution. So our original equation has one unique solution. So there is exactly one C1, C2, C3 such that this equation is true for all numbers B2, B1, B0. Because our B2, B1, B0 were arbitrary numbers, this means that every element in P2 can be written as a linear combination of our subset K in exactly one way. So K is a basis for P2. In this next exercise, we will work with the vector space C infinity, the set of smooth functions. We are given a subset and we want to show that this subset is linearly independent. We will use the same tool where we first set our linear combination to the 0 element. In this case, our 0 element is the 0 function. And then we check that these coefficients must be 0. So we now want to show that the only solution to this equation is C1 equals C2 equals 0. Unlike before, when we were working with polynomials, where we have standard forms for polynomials, we don't have a standard form for the functions in C infinity. But what we can do is that we know these are real value functions. So we can try to plug in some values into the functions and see what we get. Let's try plugging in 0. E to the 0 is 1. So we get C1 plus C2 is 0. This is good. This means that C1 plus C2 must be 0. Now let's try to plug in other numbers. The next simplest number would be 1. I get this equation. Let me now multiplied both sides by d value e. Let me now replace C2 using this equation. So C2 is equal to negative C1. So now I've arrived at this equation, but I know that the number e squared is not equal to 1. So this value cannot be 0. So this other factor must be equal to 0. So C1 must be equal to 0. And C2 is equal to negative C1, so C2 is also 0. We've shown that the only solution to this equation is C1, C2 being 0. So our set is linearly independent. So far, we have been talking about a linear combination of a finite set, but it makes sense to define a linear combination of an infinite set. We cannot add infinitely many things, but we can define a linear combination of an infinite set to be a linear combination of any finite subset of that set. Another way to say this is that it's a linear combination of the whole set, but with finitely many non-zero coefficients. All the other coefficients except finitely many of them would be 0. For the vector space of all polynomials, we will show that this set of powers of x is a basis for P. This is in fact called the standard basis for P. To show that our set B is a spanning set of the set of all polynomials, let f be some polynomial. So f can be written in the standard form for some numbers that are the coefficients for f. But just writing this down already shows that f is a linear combination of B. F was an arbitrary polynomial, and any polynomial can be written in this way as a linear combination of a finite subset of B. So B is a spanning set of P. To show that B is linearly independent in P, take any linear combination of B and set it to the 0 polynomial. So a linear combination of B would be in this form, and I set it to 0, but the only way this can be true is if each of these coefficients are 0. So our set B is linearly independent, and this shows that B is a basis for P. This is called the standard basis for the vector space P of all polynomials. In fact, many of our favorite vector spaces have simple standard bases. The standard basis vectors form a basis for Rn. So this is the one that we have been studying for a while. R3 has these standard basis vectors that form the standard basis for R3. We just saw in the previous slide the powers of x form a basis for P. And for P sub n, for a fixed n, the powers of x less or equal to n also form a basis. For example, for P4, it has this standard basis with 5 elements because we also count x to the 0. For a fixed size, the vector space of matrices of that fixed size has a standard basis where you just take the matrices with only one entry with value 1, and the other entries are 0. For example, for R2 by 2, I have the standard basis that has 4 elements, but not every vector space has a standard basis. For example, the vector space C infinity or the vector space of all sequences do not have standard bases. For the vector space of vectors, we have seen that every basis have the same number of elements. Previously, this allowed us to define dimension of a subspace. We can do the same for a vector space. Every basis for a vector space would have the same number of elements, and the dimension of a vector space is defined to be the number of elements in any basis. Intuitively, the dimension is the smallest amount of numbers that you need to describe any element in the vector space. For example, the number of numbers that you need to describe a vector of height n is n. For example, in R5, you have a vector of height 5, and you need 5 numbers to be able to describe an arbitrary element for all 5 entries. For P sub n, you need n plus 1 because the standard basis looks like this, and this has n plus 1 many elements. And also, in order to describe an element in Pn, you need to know what the coefficients of the polynomials are. For example, in P2, an arbitrary element looks like this. So you need to know what A, B, C are to describe this polynomial. And for the vector space of all matrices of the same size, if the size is m by n, then there are m times n entries in that matrix. So you need m times n numbers to describe each matrix. For example, in R, for the size 2 by 3, an arbitrary element looks like a matrix of size 2 by 3, and you need 6 entries. So you need 6 numbers at the minimum to describe an arbitrary element in this vector space. The dimension of a vector space can be infinite. If there is no finite basis for a vector space, we say that the dimension of that vector space is infinite. For example, we saw that the standard basis for the vector space of all polynomials has infinitely many elements, all of the powers of x. So P has infinite dimension. The vector space of sequences and smooth functions also do not have a finite basis, so they're both infinite dimensional. Intuitively, this says that there is no way to describe an arbitrary element using just a fixed number of numbers. This is the end of lecture 17a. In the next lecture, we will continue talking about bases and dimensions for vector spaces, and we will continue to try to generalize our tools to more general vector spaces.